Welcome back to Science Corner. You know we love diving deep into some really cool scientific topics.
Yeah.
And today we're going to be talking about something pretty fascinating.
Yeah, definitely.
Transmitting data wirelessly using light.
Uh-huh.
I mean, think Star Trek, right? But real?
Yeah, absolutely. It's like we're moving into the future.
Totally. And we're going to be focusing on a really cool development.
Okay.
The Tara chip. Have you heard about this?
Yeah. I've been keeping an eye on it. It's pretty revolutionary what they're doing over there.
It is. And for this deep dive, we've got a couple of great sources we're going to be looking at.
Okay.
So first up, we've got the Wikipedia entry on photonic integrated circuits.
Right, the foundation.
Exactly. Got to understand the basics. And then we'll be jumping into Tara's own announcement about their new chip.
Sounds good.
So the big question is, how do they actually send data through the air using light? And what makes this Tara chip such a big deal?
Yeah, well, maybe we should start with, like you said, the PICs, right?
Yeah.
Photonic integrated circuits.
Yeah, let's break it down.
So what they are essentially are, it's like, you know how we have electronic integrated circuits in our computers and phones?
Like the chips in our devices.
Exactly, yeah.
Yeah.
So they use electrons to process information.
Mm-hmm.
PICs are kind of similar, but instead of electrons, they use photons.
Okay, and photons are?
Light particles. It's like the fundamental unit of light.
So these chips are manipulating light to move information around.
Yeah, exactly.
Wow.
And these light waves, they're typically in the visible or near infrared part of the spectrum.
So like the light we can see? Or...
Yeah, some of it, yeah. But also wavelengths that are a bit longer than what our eyes can pick up.
Oh, okay.
Kind of like the invisible light that your TV remote uses.
Huh, interesting. So it's not blasting like a spotlight everywhere then?
No, it's much more targeted than that.
Okay, good to know.
And the cool thing about using light is that it allows for super fast data transmission.
Okay.
And you don't get the same kind of interference that you might encounter with radio waves.
Right, because everything's wireless these days, right?
Yeah, exactly. The airwaves are getting pretty crowded.
So using light is like opening up this whole new highway for data.
Exactly.
Got it. So then what are these PICs actually made of? Because I know computer chips are mainly silicon, right?
Yeah, that's right. But with PICs, it's a bit more diverse.
Right.
They use a wider variety of materials.
So like what else besides silicon?
Well, the Wikipedia article talks about indium phosphide, or ENP, as being really important commercially.
MP, right?
Yeah. And what makes it so special is it can both create and control light.
On a single chip?
Yeah, all on one chip.
That's pretty amazing.
It is. So you can have these active components, like lasers that generate the light.
Okay.
And then passive components, like waveguides and modulators, that kind of shape and direct the light.
So it's like a whole light show happening on this tiny chip.
Uh-huh. Yeah, kind of like that.
And so early versions of these PICs, they were already using NMP.
Yeah, they were making things like 2-section distributed Bragg reflector lasers, or DBR lasers.
2-section what?
It's a mouthful. But basically, these were like simpler types of lasers.
Okay.
But they were kind of the first step in showing that this integrated approach with NMP was really powerful.
Gotcha. So from those early lasers, how did things evolve? What do PICs look like today?
Well, we have these really sophisticated things called monolithic tunable lasers.
Okay.
So these lasers can emit light at different wavelengths. It's like having a laser that can change colors.
Wow, that's cool.
Yeah. And we also have these externally modulated lasers, or EMLs, and integrated receivers, which are super important for high-speed communication.
And all of these are built using PIC technology.
Exactly. And the Wikipedia article actually mentions that by 2012, researchers were already integrating hundreds of different optical functions onto a single chip.
Hundreds. That's incredible.
It is. The field's been moving incredibly fast.
So stepping back a bit, the whole field of photonics, it's relatively new, right? Like when did this all begin?
Well, you could say it really took off with the invention of the laser in the 1960s.
Right. That makes sense. Lasers are all about light.
Yeah. The laser gave us this really intense, focused source of light.
Which I guess was essential for developing all of these optical technologies.
Absolutely. Then, in the 1980s, we saw the rise of fiber optic communication.
Oh, yeah, using light to send information through those glass fibers.
Exactly.
Yeah.
That's basically how the modern internet works.
But it's not just about the laser, right? There were other key innovations along the way.
Yeah, definitely. I
Really?
mean, one that stands out is the work of Mentsmit at Delft University of Technology.
Okay.
He invented something called the Arrayed Waveguide Grating, or AWG.
What does that do?
It's like a traffic director for light signals.
Okay.
It can route different wavelengths of light to different destinations.
So it's kind of like a switchboard for optical communication.
Exactly.
That's pretty cool.
And it's a fundamental component in a lot of optical systems, from internet infrastructure to, well, even Taurus technology, which we'll get to later.
All right, so we've talked about indium phosphide for these PICs,
Uh-huh.
but the Wikipedia article also mentions silicon. Can you actually use silicon for photonic chips?
You can, but it's a bit tricky.
Okay, why is that?
Well, silicon has what's called an indirect band gap.
An indirect what now?
Haha. Yeah, it sounds complicated.
Mm.
But basically what it means is that silicon isn't very good at emitting light.
Ah, so it's not like a natural light source.
No, not really. It's more like a light bulb that takes a lot of effort to turn on.
Got it. So why even bother using silicon if it's not good at making light?
Well, silicon has other really useful properties for photonics.
Like what?
So it turns out that silicon is actually excellent at creating passive photonic circuits.
Passive circuits.
Yeah, these are components that can guide and manipulate light,
Okay.
but they don't actually generate the light themselves.
It's like the roads and infrastructure, but not the cars.
Perfect analogy. And silicon is really good for this because it has low losses, meaning the light signal doesn't weaken too much as it travels through the circuit.
Okay, that's important.
It is. And it's also not very sensitive to changes in temperature, which is a big plus.
So it's stable and reliable.
Exactly. Plus, and this is a huge advantage, silicon photonics allows you to integrate optical circuits with traditional electronics all in the same chip.
Oh, so you can have the light and the electronics working together seamlessly.
Yeah, that's the idea. You can have the light doing the fast data transmission and the electronics handling all the control and processing, all in one tiny package.
So it's like a hybrid approach.
It is, yeah. And that co-integration is super powerful for building more complex systems.
Right. It makes sense to combine the strengths of both.
Absolutely.
So we've talked about silicon and indium phosphide. What other materials come into play with these PICs?
Well, there's a whole bunch of other interesting materials.
Oh, really?
Yeah, like lithium niobate,
Okay.
which is great for making modulators.
Modulators, what do they do?
They basically change the properties of the light signal, like its intensity or phase.
Okay.
And that's how you encode information onto the light.
So it's like turning the light on and off in specific patterns to represent data.
That's a good way to think about it, yeah.
Okay, cool.
And then there's silica on silicon, which also has really low losses for guiding light.
And silica is just a type of glass, right?
Yeah, that's right.
Got it. So is each material used for specific components then?
Pretty much, yeah. It's like having a toolbox with all these different specialized tools.
Makes sense.
And depending on what you're trying to build, you choose the best material for the job.
Okay, so building a PIC sounds a lot more complicated than making a regular electronic chip.
Yeah, it definitely is.
I mean, in electronics, you've basically got the transistor as your main building block.
Right.
But with photonics, it seems like you need all these different components working together.
That's true. You need waveguides to act like tiny optical fibers on the chip, power splitters to divide the light signal, optical amplifiers to boost the signal strength,
Right.
modulators to encode the data, filters to select specific wavelength.
Wow, it's a lot.
It is. And of course, you still need lasers to generate the light and detectors to receive it.
So it's like a whole orchestra of components playing together.
I like that analogy.
Right.
And getting all these different components, which often need different materials and manufacturing processes to
Right.
play nicely together on a single chip, that's a huge engineering challenge.
Yeah, I can imagine.
But despite all those complexities, PICs are already playing a really important role in technologies we use every day.
Like how?
Well, the Wikipedia article mentions fiber optic communication as the main application.
Right, because those fiber optic cables use light to transmit data.
Exactly. And PICs are crucial for making that technology work efficiently.
So they're kind of like the hidden heroes of the internet.
Haha, you could say that.
Cool. And what about applications beyond telecommunications? Are there other areas where PICs are making an impact?
Oh yeah, there are tons of exciting new applications popping up.
Like what?
Well, biomedicine is a big one. PICs can be used to create super sensitive biosensors
Okay.
for things like lab-on-a-chip devices. So imagine these tiny chips that can analyze blood or other biological samples really quickly and cheaply.
That would be huge for medical diagnostics.
Absolutely. And there are also applications in creating really precise temperature sensors.
Temperature sensors using light.
Yep. And even in the automotive industry, they're being used in LiDAR systems.
LiDAR, that's for self-driving cars, right?
Exactly. LiDAR uses light to map the surroundings, which is crucial for autonomous vehicles to navigate safely.
Right. It's all about sensing the environment with light. That ties in perfectly with our main topic today.
It does.
So PICs can even be used for in-car Wi-Fi,
Uh-huh.
which is basically using light for wireless communication inside the vehicle.
Yeah, think like super fast Wi-Fi, but using light instead of radio waves.
Wow. Okay. Anything else?
Well, in engineering, they're used in fiber optic sensors that can measure things like pressure or strain in structures.
So like monitoring bridges and buildings for safety?
Yeah, exactly. And even in agriculture, they're being used to analyze things like the ripeness of fruit or the nutrient content of soil.
It's amazing how versatile this technology is.
It really is. And the field is constantly growing, with new applications being developed all the time.
So before we dive into the specifics of the Torah chip, the Wikipedia article also mentions different fabrication materials beyond ENP, like silicon nitride
Yes.
and silicon photonics.
Uh-huh.
What are the key differences between these?
Well, silicon nitride, or SIN, it's really good because it works with a super wide range of light wavelengths,
Okay,
and it has incredibly low losses when you're guiding light through it.
so less signal loss. That's good.
It is, yeah. That makes it ideal for things like detectors and spectrometers,
Okay.
which analyze different colors of light. And it's also being used in advanced biosensors and even in quantum computing.
Wow, quantum computing, that's getting pretty advanced.
It is. And then you have silicon photonics, or SIF, which, as we talked about earlier, is really good for passive components.
Right, silicon being good for guiding light but not emitting it.
Exactly. But the really cool thing about SIF is that it's compatible with the manufacturing processes
Yeah.
that are already used to make electronic chips.
Oh, so it's like you can piggyback on existing infrastructure.
You got it. That makes it much easier and cheaper to produce these photonic chips on a large scale.
Makes sense. So it's not just about the material itself, it's about the whole manufacturing ecosystem.
Yeah, exactly. And that's a big advantage for silicon photonics.
Got it. Now, before we move on to Tara, there's one last thing from the Wikipedia article I want to touch on. Hybrid or heterogeneous integration.
Okay.
What exactly is that?
So that's the idea of combining different types of chips together.
Okay.
Like you might have an ANP chip that's really good at generating light,
Right.
and you combine that with a silicon photonics chip that's great for processing the light signals.
So each chip specializes in what it does best.
Yeah, and then you package them together to create a more powerful and efficient system.
So it's like a team effort at the chip level.
Haha, that's a good way to put it.
Okay, I think we've got a good foundation now with PICs.
Yeah, I think so too.
So let's finally turn our attention to the Tera chip.
Mm-hmm.
What exactly are they trying to achieve with this technology?
So, Tara, their mission is pretty clear.
Okay.
They want to bring fast and affordable internet to people using beams of light.
Beams of light like lasers shooting through the air.
Yeah, kind of like that.
Wow.
But they're invisible and they're really focused.
Okay.
And they're especially focused on areas where traditional internet infrastructure like fiber optic cables
Yeah.
is either lacking or just too expensive to deploy.
Right, like rural communities or developing countries.
Exactly. And they've actually been working on this for a while.
Oh, really?
Yeah, they have this first generation technology called LightBridge, which they've already deployed in a few places.
So this Tera chip is like the next step in their evolution.
It is.
And the core concept remains the same, using light to send data wirelessly.
It's like creating an invisible fiber optic cable through the air.
That's pretty wild.
It is.
So how does this Tera chip improve on their earlier LightBridge system?
Well, LightBridge relied on physical steering to aim the light beams.
Okay.
So they used mirrors, sensors, and all this mechanical hardware to track and align the beams.
So it was kind of bulky and complicated.
Yeah, it was. But the new chip, it does away with all those moving parts.
Oh, wow.
It uses software to steer, track, and correct the light beam.
All through software.
Yeah, isn't that amazing?
It's a huge improvement.
It is. It makes the system much smaller,
Okay.
more energy efficient, and easier to deploy.
That makes sense. And their announcement even says they've shrunk the functionality of a LightBridge unit, which was like the size of a traffic light,
Yeah.
down to a chip the size of a fingernail.
It's incredible, right?
Yeah, that's miniaturization on a whole other level.
It is. And it's not just about size. It's also about cost and power consumption.
Right, so making it more affordable and accessible.
Absolutely. Tara also talks about the ever-increasing demand for data worldwide.
Yeah, everyone's streaming and downloading more and more.
Exactly. And that's putting a lot of strain on our current infrastructure.
Mm-hmm.
Like laying fiber optic cables, it's expensive and
And
time-consuming.
not always practical in every location.
That's right. And then there's the radio frequency spectrum, which is getting super congested.
So we're running out of space for all our wireless signals.
Pretty much. But light offers this virtually unlimited bandwidth.
It's like opening up a whole new dimension for data transmission.
Exactly. So Tara's original light bridge, it sent these narrow, invisible beams of light through the air,
Okay.
and they could achieve speeds up to 20 gigabits per second.
That's really fast.
It is. And it could do this over distances of up to 20 kilometers.
Wow. But how do they actually aim and maintain those light beams so precisely over such long distances?
So it was this really sophisticated system. Okay. They used mechanically controlled mirrors, highly sensitive sensors, and special optics.
Okay.
And they had software that controlled all of this, making tiny adjustments to keep the beam perfectly aligned.
Sounds complicated.
It was, and that's why the Tara chip is such a game changer.
Because it gets rid of all those moving parts.
Exactly. So the Tara chip uses something called an optical phased array.
Optical phased array, what is that?
Think of it like a tiny grid with hundreds of tiny light emitters.
Okay.
And the software can control exactly when each emitter turns on and off.
So it's like a chorus of tiny lights all singing together.
That's a good visualization.
And by controlling the timing of these emitters, they can manipulate the light beam.
That's right. They can steer it electronically without any physical movement.
It's like a virtual antenna for light.
Yeah, that's a great way to think about it.
So they've essentially replaced all the complicated mechanics with clever software and this phased array.
Exactly. And they've already tested this technology outdoors at their Moonshot factory labs.
And how did the tests go?
Really well. They were able to transmit data at 10 gigabits per second over a distance of 1 kilometer.
And this was all using silicon photonics.
Yeah. They say it's the first time anyone's achieved this kind of performance with silicon photonics in an outdoor setting.
That's a pretty big deal.
It is, yeah. And they're not stopping there.
What are their future plans for the chip?
Well, they want to increase the range and capacity even further.
Okay, how are they going to do that?
By packing even more emitters onto the chip. They're talking about thousands of emitters.
Wow, so even more tiny lights.
Yeah. And with more emitters, they can get even more precise beam steering.
Okay.
And potentially even higher power output.
So they can send data over longer distances and at even faster speeds.
Exactly. And this all goes back to what we talked about with PICs earlier.
Right, the fundamentals of manipulating light on a microscopic scale.
Yeah. The Tara chip is a perfect example of how this technology can be used to solve real-world problems.
And they're not just focused on internet access, right? They're talking about other applications too.
Yeah, they're thinking big. They envision this global mesh network
Right.
that could connect everyone everywhere.
That would be incredible.
It would. And they're also talking about rethinking data centers,
Okay.
making them faster and more energy efficient.
So it's not just about connecting people, it's about connecting everything.
Right. And they even mention using this technology for communication through autonomous vehicles.
So like cars talking to each other using light.
Yep, that's the idea. And with super fast and reliable communication, self-driving cars could become even safer and more efficient.
It's mind-blowing to think about all the possibilities.
It really is.
And this isn't just some far-off sci-fi concept, right? They're actually planning to release a product with this Tara chip pretty soon.
Yeah, they're aiming for 2026.
That's just a couple years away.
I know, it's really exciting. And they're encouraging researchers to explore new applications for the technology as well.
So they're really opening it up to the world.
They are. They see the potential for this to be much bigger than just what they're doing with it.
So to sum it all up, the Tara chip, it's a major step forward in taking this complex science of photonics and turning it into a practical solution for a really important problem.
It is, yeah.
The need for faster, cheaper, and more accessible internet for everyone.
Exactly. It's a great example of how scientific research can lead to real-world innovations.
And it really makes you think about what the future holds for this technology.
Absolutely. I mean, if we can send data through the air using light, who knows what else we might be able to do.
Right. What other limitations we might be able to overcome.
It's a whole new frontier.
It is, and it's definitely an exciting one. Thanks for joining us today and shedding light literally on this amazing technology.
My pleasure. It was a great conversation.
And for our listeners, keep those minds curious, and we'll see you next time on Science Corner.